Okay. Yeah, this is the topic for today's class. In R2, let me draw an XY plane. XY plane. In R2, any 2 points, there is a distance, and any vector, right? Any vector. The vector has a length, and any 2 vectors in R2, between the vectors, there are 2 angles. Yeah, this angle and this angle. But usually, when we say that the angle between 2 vectors, we mean the smaller angle, the angle between 0 degree and 180 degrees. When the angle is 90 degrees, we say that these 2 vectors are orthogonal to each other. This is in R2. Now, in Rn, we cannot plot points and vectors in Rn. Then, how to determine the distance between 2 points, say, in Rn? How to find out the length of a vector in Rn? Now today, I want to answer this question. Okay, now I want to extend the concepts of distance, length, orthogonality, and angle in R2 to Rn today. Okay. First, let me extend the distance from R2 to Rn first. Number 1, length, distance. Length V is components U1, U2, and second point in R2. Take a review about the formulas between 2 points in R2. Here, in this book, in this course, a vector and a point, they are the same, okay? They are identical. The formula to compute the distance between the 2 points is distance between the point U and the point V. The formula is x coordinate minus x coordinate U1 minus V1 square plus U2 minus V2 square, then square root. Now the question is how to get this formula. Yeah, this is an XY plane. Suppose the point U is here. This is a U1, U2. The second point is here, V1, V2. Why? The distance between these 2 points is this number 1 by pi diagram theorem. Okay, let me draw a right triangle. Yeah, through this point, let me draw a line parallel to the x-axis, and through this point, draw a line parallel to the y-axis. Then we have a triangle. Yeah, A, this point, B, this point, C, this point. The length of AB from A to B, what is the length? What is the distance? It is a V1 minus U1, right? V1, the x coordinate of point B. U1, the x coordinate of point A. So V1 minus U1 is the distance between the point A and point B. And the distance between C and B is a y coordinate, V2, minus the y coordinate of the point A, U2. Yeah. So this is a right triangle. Okay. Yeah, this angle is 90 degrees. So by pi diagram theorem, so the length of AB, AC, not AB, AC, yeah, the length of the hypotenuse of the triangle square is equal to the length of AB square, V1 minus U1 square, then plus the length of BC, V2 minus U2 square. So take square root, we have this formula. The distance between this point and this point is given by this number, by pi diagram theorem. Okay. Now, this is the formula to compute 2 points in R2. Now, in Rn, we cannot plot the points in Rn. Then, how to know the distance between 2 points in Rn? The formula, extend this formula. Yeah, on next page. Now, let U be this point, U1, U2, and UN. Yeah, this is a point in Rn. A second point, V1, V2, Vn, also in Rn. Now, the distance between these 2 points, because we cannot see the points, so we have to specify the following number as the distance between these 2 points. We define the distance between point U and point V by this formula. First, entries are U1 minus V1, the difference between U1 and V1 square, plus second entry U2 minus V2 square, and so on. UN minus Vn square, then take square root. Yeah, we use this number as the distance between these 2 points in Rn. Okay. Yeah, this is the extension of the length, the distance from R2 to Rn. Now, second, let me see. Second, the length of a vector. Okay. Number 2, the length of a vector. All right. First, in R2, say we have a vector. Okay, a vector V. Say this vector x coordinate is V1, y coordinate is V2, this vector. Okay, now the length of this vector, the rotation, the length rotation, yeah, the both use this rotation to denote the length of a vector. Yeah, this rotation. Clearly, the length of the vector is the distance between the origin and this point, right? This is the distance between the origin and the point V. By distance formula, it is 0 minus V1 squared. First entry minus first entry t squared. Then second entry of the 0 vector minus the second entry of the V vector. So it is V1 squared minus V2 squared. Yeah. So the length of a vector in R2, the formula is this. Now, let me expand this concept of length from R2 to Rn. Now, in Rn, because we cannot see a vector in Rn, so we have to define, specify a number, give a number to the vector in Rn as the length. We define, okay. Vector in Rn by this formula. First entry of vector V square plus second entry square plus and so on. The last entry square, then take square root. Yeah. As the length of V. Yeah, V entries are this in Rn. Yeah. This is the length in Rn. This rotation means the length of vector V. By the length rotation, we can write the distance formula as here vector U, vector V, vector U minus vector V is equal to U1 minus V1, U2 minus V2, UN minus VN, right? The difference of two vectors. So take a look. This sum, then take square root. Actually, this is the length of this vector. U minus V is a vector. The length of this vector is the distance between vector U and vector V. Yeah. So we can use the length rotation to rewrite the distance formula. Yeah. The distance between U and V actually is U minus V. This new vector, the length is the distance between U and V. Okay. Yeah. Let me take a look at some examples. Examples about these formulas. Examples. Example one. Example one. Let V be 1, -2 to 0. It is a 4-dimensional vector. We cannot plot this vector in R4 because we cannot draw the space R4, right? Okay. Now the question is find a unit vector. What it means, a unit vector. A unit vector has length 1. Okay. When the length of the vector is 1, we call the vector a unit vector. Okay. A unit vector. Find a unit vector. Okay. 2 parts in the same direction. A vector has a direction. In the same direction as vector V, part 1. Second part. In the opposite direction as vector V. How to answer these 2 questions? The given vector V, its length may not be 1. Okay, let me compute the length of the vector first. Now compute the length. Yeah, length, rotation. By formula, the length, go back to the formula. In Rn, the length of a vector is given by this number, Okay. Yeah. So it is a square root. First entry, take square, plus second entry, take square, and then third entry, square. The last entry, square. Then calculator. It is 1 plus 4 plus 4 square root. It turns out that the length of this vector is 3, even though we cannot see this vector, but by formula we can still tell the length is 3. Okay. All right, now let me answer the first question. Number 1, unit vector. Okay, let me divide this vector by its length. This vector over the length of the vector. This should be a unit vector. The length of this vector should be 1. Okay. So this is a 1 over 3, right? The length is 3. Then times the vector. Okay, multiply the number to all the entries, 1/3, 2/3, 2/3, 0. Yeah. This vector is a unit vector and in the same direction as the vector V, because I multiply the vector by a positive number that doesn't change the direction. Number 2, how to find a unit vector in the opposite direction as the vector V? Yeah, let me use this unit vector, but let me add a minus sign. Minus change the direction. Add a minus sign. Okay, add minus sign to all the entries. -2/3 and then 0. Yeah. This vector is a unit vector and in the opposite direction as the vector V. Yeah, done. This is the answer to this example. Okay. Now, second example. Second example. Yeah. Example 2. Example 2. So that a number, a scalar times a vector. We have a new vector. Then the length of this new vector is equal to absolute value of the scalar, because the length is a non-negative number. So when we move C out, we need to add absolute value to guarantee the scalar non-negative. I move C out, remember, add absolute value, then times the length of vector V. Okay, well, where C is a scalar. Yeah, scalar. Scalar means a number. In linear algebra, we usually call numbers scalars. How to see this formula? Yeah, how to see this formula? And let vector V be V1, V2, and Vn. Yeah, it is a point in Rn. Then C times vector V is C times all the entries. Okay. So the length of C times V by formula, it is first entry square plus second entry square by formula. C times Vn square by formula, square root. Okay, square root. All right, now let me rewrite the sum. C, a number times a number, then take square is a C square times V1 square plus C square times V2 square, and so on. Then take square root. Hey, now let me factor C square times V1 square, V2 square, Vn square. Okay. Now move C square outside the square root. Don't forget absolute value. Yeah. So, but this square root is the length of vector V. So we have absolute value of C times the length of vector V. So we have this equation. So done. The proof is done. Okay. At this point, we have extend the distance and the length from R2 to Rn. Now, next, let me extend orthogonality between two vectors in R2 to the orthogonality between two vectors in Rn. Okay. Yeah, let me extend the concept of orthogonality from R2 to Rn. Okay, before I do the extension, let me introduce inner product, this concept first. Okay, inner product first. Yeah. Number 3. Inner product. Here is the definition. And then vector U, U1, U2, and UN. Yeah, this vector is in Rn. And vector V, V1, V2, and Vn. Also, this vector in Rn. Okay. Then the inner product. Okay. Some people call inner product dot product. Okay. Then the inner product of vector u and vector v is the following number. Okay, yeah. The notation inner product is a u dot v. Yeah, inner product. It is a number. What number? It is the number is u1 times v1 plus u2 times v2 and so on. Last entry un times last entry. Yeah, this number is called the inner product of vector u and vector v. Yeah, so inner product is a number. Okay. Remark. If we view vector u and vector v as n by 1 matrix, n by 1 matrix, then u transpose n by 1 matrix, take transpose is a 1 by n matrix. Then 1 by n matrix times n by 1 matrix. Yeah, this guy is 1 by n. This guy is n by 1. So the product is 1 by 1. Okay. Yeah. The product is a 1 by 1 matrix. Yeah. Let me compute this 1 by 1 matrix. U transpose V. It is a U. It is a column vector. Column vector is n by 1. Take transpose 1 by n. So U1, U2, and UN. Yeah, this is a U transpose. Now times vector V, V1, V2, Vn. Vector V is a column vector, n by 1 matrix. Now compute this product by row column formula. It is a U1 times V1 plus U2 times V2 and so on. UN times Vn. Yeah, 1 by 1 matrix. So compare this number and this number. Actually, they are the same number. So the inner product, it is a number. Okay. The inner product of U and V. Yeah, inner product is this number. Is the 1 by 1 matrix U transpose times V without the brackets. Yeah, if we remove the brackets, then only the number is inner product. So inner product actually is U, this vector transpose times the vector V. Yeah, the vector V. Okay. Okay. Now, now we have we just learned in terms of inner product. Okay, in terms of inner product. Right. The length formula first. Length formula. Let me see. I don't remember the length formula. Go back. Okay. The length formula. Yeah, here. The length of a vector, the formula is this. Okay. Yeah. Square root u v1 square, v2 square, and vn square. The length. But u1 square, v1 square, v2 square plus vn square. It is vector v dot itself. You agree? Inner product of the vector v with itself. It is this number. So the length of a vector is square root of the inner product of the vector with itself. With itself. Yeah. Remember this formula. We often use this formula. Okay. We often use this formula. Keep this formula in mind. Okay. Or you can take square on the both sides. Same formula actually. Yeah. The length square is vector v dot itself. Yeah. These two formulas we often use. How about distance formula? In terms of inner product. Yeah. Yeah. Distance between u and v. The formula is, let me see. Distance. Distance between u and v is this number. This number actually is the length of the vector u minus vector v. Okay. This is a vector u minus vector v length. Okay. Now, by the formula here, then it is a square root u minus v dot itself. So we can write the length in terms of inner product and the distance in terms of inner product. But this formula or this formula we often use. Keep these two formulas in mind. Okay, in mind. Okay, now let me show you examples. Okay. About inner product. Example number 3. Let vector u be 2, -5, -1. 3-dimensional vector. And vector v be 3, 2, -3. Now the question is, compute u dot v and v dot u. Okay, compute these two numbers. All right. Now, by formula, u dot v inner product is first entry times first entry plus second entry times second entry plus third entry times third entry. Then calculator -1. Then how about v times v dot u? V dot u. It is first entry times first entry plus second entry times second entry, 2 times -5, then plus third entry times third entry, again, -1. So we conclude that U dot V, this number is equal to V dot U, this number. Yeah. We can switch U and V and don't change the numbers, don't change inner product. Example 3, example 4, also about inner product. Example 4. Let U be -1, 2, a 2-dimensional vector. We can plot this vector in XY plane. V is 2, 3. Also a 2-dimensional vector. Okay, now compute. Okay. U dot V, inner product between the two vectors. Inner product is a number. Yeah, this is a number. Then over V, the length square. A number over a number, it is a number. So this is a number. Then times vector V. Now, how to find this vector? A number times a vector is a vector. Okay, now solution. Okay, now let me compute U dot V, inner product. By formula, first entry times first entry plus second entry times second entry. So it is a 4, number 4. Next, compute the length of vector V. The length of vector V, by formula, it is vector V here. It is 2 square plus 3 square root. Okay, so it is square root of 13. Therefore, so length square here, take square on the length, it is equal to 13. So this vector U dot V over the length of V square times V, it is inner product is 4 over the length square is 13 times vector V. Vector V is 2, 3. Now multiply this number to all the entries. We get 8 over 13, first entry. Then 12, right? 4 over 13 times 3, 12 over 13. And yeah, this vector is this vector. About inner product. Let me present some properties. Okay, some properties. Okay. Number 1, U dot V is equal to V dot U. Yeah. We saw this property in the previous example, right? This number is equal to this number. B, U plus V, it is a new vector. Then dot W, it is equal to, we can distribute the W to U and V. It is equal to U dot W plus V dot W. Okay, distribution. Yeah. C, a number times U, then dot W. It is equal to U dot W first, then multiply by the number C. Okay. And also we can move C to W. Okay. Yeah. Same. Okay. Same. D, a vector dot itself. It is by formula first entry square times second entry square, and so on. Yeah, a vector dot itself. This number clearly non-negative. So a vector dot itself is a non-negative number. Yeah. E, a vector dot itself. Yeah, it is this number. A vector dot itself is equal to 0 if and only if the vector is a 0 vector. Yeah. A sum of non-negative numbers is 0. Then all the non-negative numbers must be 0. That means that all the entries of vector U is 0. Reversely, if the vector U is 0, 0 vector dot itself is a 0 number. So we have if and only if. Yeah, two directions. Two directions. From here, we have this equation. From this equation, we have this equation. If and only if. Okay, now after I introduce inner product, I am ready to extend orthogonality from R2 to Rn. Now, okay. This is orthogonality number 4. Orthogonality. Okay. First, consider two vectors in R2. Okay. In R2 first. Then extend orthogonality from R2 to Rn. Okay. In R2, we have two vectors. Vector U orthogonal to vector V. Okay, let me draw a diagram because in R2 I can draw a diagram. Okay. R2. This is 0. Okay. Vector U here. Vector V here. They are orthogonal. That means that this angle 90 degrees. Okay. A vector is orthogonal to another vector if and only if let me this is a vector U, vector U. Let me turn the vector negative U. Vector negative U is here. Yeah, negative U. Yeah, negative U. Yeah. Okay, when vector U is orthogonal to vector V, the distance between U and V. Yeah, distance between U and V is this distance. Is equal to the distance between negative U and V. You agree? Yeah. When vector V orthogonal to vector u, then this distance is equal to this distance. Yeah. If you don't believe, you can draw a second diagram. Say here, u. Now v. This time v is not orthogonal to vector u. Let me draw negative u here. Negative u here. Because now this time u is not orthogonal to v. The distance between u and v now this time not equal to the distance between u and negative v. So u orthogonal to v if and only if this distance is equal to this distance. Okay. Now by distance formula, okay, this distance is equal to remember u and v now in R2. By formula, it is a first entry minus first entry squared plus second entry minus second entry squared. Yeah, this is the distance. How about this distance? Now this time, negative u is negative u1, negative u2, right? Negative u. Okay. Now, distance between this vector and u is negative u1 minus v1 squared plus negative u2 minus v2 squared. Okay, now let me remove the square root by taking square on the both sides. So we have this equation. Is equal to negative u1 v1 squared plus negative u2 v2 squared. Okay, now let me expand the square. Okay, this guy expanded u1 squared minus 2 u1 v1 plus v1 squared, then plus expand this square u2 squared minus 2 u2 v2 plus v2 squared. Okay, how about let me erase these two diagrams. All right. Okay, now here is equal to expand this. Okay, expand this. It is a negative u1 squared 2ab, so plus 2 u1 v1, then plus negative v1 squared. Same, expand this. Okay, negative u2 squared plus 2 u2 v2 plus negative v2 squared. Okay, now here let me continue here. Here, let me change back to the black color. Here. All right. Simplify this equation. u1 squared negative u1 squared cancel. v1 squared cancel. u2 cancel. v2 cancel. So we have the left side is a 2 u1 v1 minus 2 u2 v2 is equal to the right side 2 u1 v1 plus 2 u2 v2. Now I move the left side to the right side, so 0. It is a 4 u1 v1 plus 4 u2 v2, and divide the equation by the number 4. So we have u1 v1 plus u2 v2 is 0. Do you recognize this number, what this number is, inner product, okay, inner product, okay. Yeah. This number actually is vector U dot vector V is 0. So in R2, two vectors are orthogonal if and only if the inner product of the two vectors is 0. Okay, 0. Okay, now because of this observation, then we can tell two vectors in Rn when the two vectors in Rn is orthogonal. Okay, now here, yeah, because we cannot see vectors in Rn, so what we can do is define. Okay, define. Okay, definition. Let me use black definition. Two vectors U and V in Rn are orthogonal when they are orthogonal. We cannot plot the vectors. How to see? If their inner product is 0, then we consider these two vectors are orthogonal. Okay, so definition. Okay, okay. So let me show you examples. Example. Example number 5. Yeah. 0. This vector is orthogonal to any vector V. Of course, these two, this is in Rn. This is in Rn. Okay, in Rn. Why? Why 0 vector is orthogonal to any vector V? Go back to the definition. Okay, let me compute the inner product of 0 vector and the vector V. Okay, by formula, inner product, first component 0 times first component of V, V1, plus second component times second component of V, and so on. These are just numbers. 0, this number times this number, 0. So 0. Therefore, because inner product is 0, 0 this vector is orthogonal to vector V. Done. Done. By definition. Okay. Example number 6. Number 6. Determine whether the vectors, the following vectors, vector U, 3, 2, negative 5, 0 are 4-dimensional. We cannot plot this vector. Vector V, whether these two vectors are orthogonal. Okay. Now, solution here. Solution. Here, solution. How to tell these two vectors are orthogonal or not? Compute inner product. Compare U dot V by formula, first entry times first entry plus second entry times second entry, plus third entry times third entry, 2, not 3, then plus 0 times 6. It turns out that calculator, 0. So conclusion, vector u is orthogonal. This notation v. Even though we cannot see them, but they are orthogonal. Done. Example number 7. Example number 7. In R2, we have pi diagram figure in R2, right? R2 pi diagram figure, right? A right triangle, right? A, B, C. C squared is A squared plus B squared. In Rn, we also have pi diagram figure. This is an example number 7. Should be number 7. Okay. Two vectors u and v in Rn are orthogonal if and only if the pi diagram formula holds. Okay, holds. U plus v, the length square is equal to u, the length square plus v, the length square. Why this equation is pi diagram theorem? Let me. Okay. Of course, we cannot plot vectors in Rn, but still, okay. Imagine that this is a Rn. Okay. Vector u here. Vector v, when vector u, vector v orthogonal, we have pi diagram theorem. Okay, orthogonal. Vector v. Now, let's see what is u plus v. Draw parallelogram. This is a u plus v. U plus v. Okay. Now consider this right triangle. This edge, the length is u. And the hypotenuse is the length of u plus v. How about this edge? What is the length of this edge? This edge, the length is the length of vector v. Vector v. So this equation says that when u and v are orthogonal, orthogonal. So this triangle is right triangle. So this equation left hand side is square of hypotenuse is equal to square of the bottom edge plus square of the height. This is a pi diagram figure. But now, of course, in Rn. Okay. Now, how to solve? Okay. U and V are orthogonal if and only if pi diagram theorem holds. How to solve? Okay. How to prove solution? Okay. Let me start with the right side. Right side. Okay. We often use. I mentioned that we often use one formula. This formula. Okay. We often use. The length of a vector is square root of the vector dot itself, or the same formula. The length square is equal to inner product of the vector. Okay, we often use these two formulas, so keep them in mind. Okay, now this equation is true if and only if U plus V dot U plus V, yeah, left side, is equal to, how about this? This is a U dot U plus V dot V, okay? Now, let me simplify this equation by distribution, 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 distribution. Then we have U dot U plus U dot V plus V dot U plus V dot V. Left side, right side, U dot U plus V dot V. Okay. Inner product is a number. Okay. So let me cancel numbers. This number cancel. This number cancel. How about this number? U dot V, V dot U. They are the same number. Okay. So we have 2U dot V is equal to 0 because the right side is 0. So if and only if U dot V is 0, move the number 2 to the right side. But whenever inner product is 0, we consider the two vectors orthogonal. U is orthogonal to V. So we prove this. Okay. Yeah. If and only if in notation is this. Yeah. So this equation is true if and only if U is orthogonal to V. When vector U and V, they are not orthogonal. They are not orthogonal. They are not orthogonal. So this triangle is not a right triangle. For a general triangle, okay, A, B, C, we usually don't have this equation, don't have pi diagram here. Only when this triangle is a right triangle, we have pi diagram here. Okay. I'm done the extension of I'm done. Okay. Orthogonality. I'm done. Okay. Now let me extend angle from R2 to Rn. Okay. Angle. Okay. Angle. Number 5. Angle. Angle. Okay. Two non-zero vectors in R2. Okay. Yeah. Let me emphasize these two vectors are non-zero. Yeah. Non-zero. If one vector is 0, low angle, say 0 here, then vector U. Then what is the angle between the 0 vector and vector U? Low angle. Okay. So here, non-zero. Let me emphasize this. Only when the vectors are non-zero, they have angle. Okay. Yeah. Actually, they have two angles. This angle. Let me use red. This angle, and also this angle. Two angles. Usually, when we say that the angle between the two vectors, we mean the smaller angle. Yeah. Let me call this given name, theta. Yeah. Theta between 0 and pi. Pi is 180 degrees. Yeah. When we say that the angle between two vectors, we mean the smaller angle. Yeah. how to define angle in RN? First, let's study the angle in R2. In R2. In R2. In R2, and let U non-zero be non-zero. Okay. Non-zero. Okay. Yeah. Then and let theta be the angle between them. Okay, between them. Okay, now because in R2 we can plot the vectors. Yeah. Zero origin here, vector U here, and vector V here, vector V. Now angle is here. Now let me make a triangle. Let me join this point and this point with a line. Then we have a triangle. Okay. Okay. The length of this edge is the length of vector V, low power. Okay. The length of this edge, yeah, this triangle, this edge, the length, low power is V. Okay. Now the question is, what is the length of this edge? What is the length of this edge? It turns out that the length of this edge is U minus V. Then take length on this new vector. How to see? The length of this edge is U minus V. Okay, now let me plot U minus V. U minus V, negative V. Yeah, negative V is here. Negative V is here. Negative V. So U minus V actually is a U plus this blue vector. Yeah, draw a parallelogram. So yeah, this blue vector is U minus V. Yeah, okay. Compare this green line and this blue line. Actually, they have the same length. So therefore, the green line, its length is the length of this blue vector. So we have this. Okay, now in trigonometry, we know that we have law of cosine. Take a review. What is law of cosine? A general triangle. Yeah, triangle. You remember that? A general triangle. Yeah. Let me call this angle theta. And this is the length of this edge is A. And the length of this edge is B. And this edge is opposite to the angle theta. Let me call it C. Yeah, we have a formula. Law of cosine. This is in trigonometry. Okay, it says that C squared is A squared plus B squared minus 2AB times cosine theta. Okay. Now I apply law of cosine to this green triangle. Okay, then by law of cosine, theta opposite side is U minus V square, C square. Then it's equal to this edge square. How about this edge first? U, the length square plus V square minus 2AB U length times V length. Then cosine theta. Theta is the angle between U and V. Okay. Now, this is from law of cosine. Now let me simplify. Okay, simplify. Again, use this formula. We often use this formula. Okay, so left side is U minus V dot U minus V. Right side U dot U V dot V. But now for these two lengths, we keep them. Okay, we keep them. V cosine theta. Okay. Now distribution. Distribution. Then we have U dot U minus U dot V minus V dot U plus negative V dot negative V. So V dot V. This is the left side, right side. No, here is a V dot V. Then minus 2 U, the length, times V, the length, cosine theta. Now let me cancel out this number cancel, and this number cancel. Okay, so we have U dot V is equal to V dot U. So this is a negative 2 U dot V, left side. Right side, only this term left, negative 2 U times V, the length, then cosine, the angle. Continue here. Continue here. Here, continue here. So if and only if, cancel negative 2 U dot V is length V, then cosine. Then move this length to the left side. Then we have this formula. U dot V over U. Yeah, this formula. Yeah. Yeah. Remember this formula. In next class, we repeat this formula, but without this derivation. Okay. Yeah. This formula is true. Okay. True in R2. Okay. In R2, any two vectors U and V, their angle, cosine the angle is equal to inner product of the vectors, then divided by the length of vector U times the length of vector V. Remember this formula. This is in R2. So in the next class, I use this formula to define the angle between two vectors in Rn. Yeah, let me stop here.